Good afternoon, everybody. This is Chaopeng Shen, hosting this exciting series on, recent advances in big data machine learning in hydrology. And today we're lucky to have Mr. Guoqiang Tang from Tsinghua University to talk about exploring deep neural networks to retrieve rain and snow in high latitudes. So I first got to know this work from a WR paper. This seems very promising as a data to prepare information for our hydrologic models and other uses. So Guoqiang Tang is now a PhD student at Tsinghua University, but he's going to graduate very soon. So congratulations ahead of time, and he's scheduled to move to Saskatchewan to work with Martin Clark. Correct? So without further ado, let's give the mic to Guoqiang. Please go ahead.
Okay, so hi everyone. I'm Guoqiang Tang from the Department of Engineering in Tsinghua University. And I'm glad to have the chance to share my experience of using deep learning techniques to retrieve precipitation in the web seminar. The title is Exploring Deep Neural Networks to Retrieve Rain and Snow in High Latitudes using Multi-Sensor and Reanalysis Data. The presentation is mainly based on two papers published on water resources research, which will be introduced in the following slides. First, let's clarify some definitions of artificial intelligence, machine learning, and deep learning. Artificial intelligence represents intelligence exhibited by machines, and a more broad definition could include any simulation of human intelligence. AI has a really long it's not a very new thing. Since the development of the digital computer in 1940s, the discussion and the application of AI based on computer programming become practical. The word artificial intelligence was proposed by John McCarthy in 1956. Machine learning is a branch of AI, and it is a way to realize AI. The basic premise of machine learning is to build algorithms that can receive input data and predict output data, and then update outputs as new data becomes available. Deep learning is a subset of machine learning, and it becomes very popular in recent years due to its power in solving some traditionally difficult problems. It contains various tasks with large amounts of data. Typical examples include deep neural networks, recurrent neural networks, convolutional neural networks, and generative adversarial neural networks. This slide shows four famous events in the history of machine learning. In 1997, Deep Blue, which is a chess-playing computer developed by IBM, defeated the best chess player. In 2005, an autonomous car named Sunny, built by the Stanford racing team, was awarded $2 million because it completed the 132-mile Grand Challenge course for the first time. In 2011, a question answering Watson, developed by IBM, won $1 million in chapter issue, and in 2016, the AlphaGo, developed by Google DeepMind, became the first AI robot that can defeat Go champion. This event shocked the world and shows the power of deep learning again. As shown in the figure on the right hand, the number of neural network types grow exponentially, which enables machine learning techniques to solve different kinds of problems. The right figure is a wonderful cheat sheet on neural network topologies. If you are not new to machine learning, you should have seen it somewhere before. There are numerous tutorials and examples on the internet, and it actually is not very difficult if you want to master a specific deep learning technique. But the real problem is to find the appropriate method that is suitable to our research fields. Another interesting example of machine learning is SCRGene, which is a program that can generate random computer science research papers. These papers will include graphs, figures, and citations. It uses a handwritten context-free grammar to form all elements of the paper. All you need to do is type in 5 optional author names, and one paper generated by this system was accepted by a conference in 2005. A deep learning framework is an or tool which allows us to build deep learning models easily and quickly. For researchers who want to apply deep learning techniques, it is actually unnecessary to get into the details of algorithms. We don't need to do everything. Many deep learning frameworks have been developed, such as TensorFlow, Keras, PyTorch, Caffe, and Deep Learning 4G. According to statistics, TensorFlow is the most popular framework among industries and researchers. And besides, most deep learning papers in earth science are based on TensorFlow. Other frameworks also have their own advantages, but we won't go into too many details in this presentation. For example, Keras can run on top of TensorFlow, and it is suitable for learning because it is relatively easy to master. Besides, I also want to mention MATLAB. As we all know, MATLAB has distinct advantages and disadvantages, and it is expensive for individuals. But for new learners, it will be very easy and fast to build deep learning models such as RN and CNN use MATLAB. Machine learning techniques have been used in precipitation estimation for decades. A typical example is Persian. This algorithm was developed by University of California, Irvine. The three most typical products are Persian CCS, and Persian CDR. Passive wave precipitation estimates are used to train infrared brightness temperature in the global scale. Therefore, the infrared products have high spatial and temporal resolutions and very long history. Recently, deep learning techniques have been used to further improve Persian precipitation estimates. I think Professor Colin Xu, the speaker in next week, who is also a major developer of Persian, will give more detailed introduction. So I won't go deep into Persian. As we all know, precipitation is one of the most important components in water and energy cycle. There are three main measurement approaches, including rain gauges, ground radars, and satellite. The phase of precipitation is categorized into rain, snow, and a mix of both. Precipitation phase has an important effect on hydrological processes. As the climate is getting warmer, less precipitation may fall as snow that may cause a profound impact on snowpack and stream flow. As a result, water availability and food security are also threatened in regions where rivers are mainly fed by snow and ice melt. Due to the limited coverage of meteorological stations and weather radars, Satellite remote sensing is the main observational source to acquire global precipitation data. Ground-based rain gauges provide the most accurate ablation. Gauges were even installed in more than 100 years ago. The figure shows the distribution of rain gauges used by GPCC products. For version 2011, more than 67,000 stations are available. The number sounds big, which however is still not enough because there are uneven distributions. Besides, rain gauges have other disadvantages as shown in the table. Weather radars are also an important source of meteorological data. However, most radars are distributed in regions with large population and developed economy, which are not enough to cover the globe. The figure shows the next radar system consisting of more than 100 S-band Doppler weather radars. Several high-quality precipitation datasets have been developed based on this system. But for undeveloped regions, radars are scarce. Therefore, the only practical way to achieve comprehensive estimation of precipitation on a global basis relies on Earth observation satellites. Their advantages include spatial temporal continuity, wide coverage, strong consistency. However, satellite observations contain large uncertainties. Algorithms and products need continuous validation and improvement. This slide introduces the three main types of satellite precipitation, which is an important background of this study. Algorithms based on infrared data build the relationship between cloud top brightness temperature and precipitation. Generally, colder clouds mean larger precipitation. However, such relationship is not so robust, and the IR-based precipitation estimates are not so accurate in most cases. Compared to IR, microwave provides more direct and accurate precipitation measurements because of its sensitivity to precipitation particles. Active microwave sensors, which are also called the spaceborne radars, often provide more direct and accurate precipitation estimates than passive microwave sensors. Algorithms combines the advantages of infrared and microwave to produce global products. A typical example is GPM Emerge, which is built on the advances in previous algorithms and produces level 3 rain and snow estimates at 0.1 degree and 30 minutes resolutions. As we have mentioned, spaceborne radars can provide the most direct estimates from space. So far, there are totally 3 spaceborne precipitation radars. They are TrimPR, launched in 1997, CUAHSI CPR, launched in 2006, and GPM DPR, launched in 2014. The CPR is capable of observing snow. CPR shows good performance for light snow, but worse performance for heavy snow due to signal attenuation. GPM DPR also has the capability of detecting snow, but relevant algorithms and products are still immature. Another instrument carried by GPM satellite is the microwave imager, shortened as GMI. The table shows some specifications of the radar instruments. GPM DPR operates at Ka and Ku band with a horizontal resolution of 5 kilometers Trim PR operates at Ku band with the same horizontal resolution with GPM DPR. CloudSet CPR operates at W band and with a horizontal resolution. CPR is the latest scanning radar, and samples are very limited compared to the other two sensors. CPR is sensitive to light precipitation and can observe snow due to its high frequency. Therefore, CPR can be used as benchmark for the assessment of other sensors, including PR and DPR. Current studies still have some limitations. Also, most satellite retrieval algorithms perform reasonable well for rain estimation. They are not satisfying for snow estimation, particularly over snow-covered or iced surface. High-frequency bands of passive microwave can be used to detect snowfall based on the scattering effect of ice, and several retrieval algorithms have been developed. However, some factors limit the accuracy of snow estimation based on high-frequency passive microwave data. First, the emission of cloud liquid water could mask the scattering signature of ice hydrometers. Second, frozen land surfaces are characterized by increasing emissivity, which could obscure the depression of microwave signal caused by scattering. Another problem of satellite precipitation retrieval is the poor quality in high latitudes. High latitude regions have a strong response to climate change than other regions. The large fractions of snow-covered surface and frequent snowfall mainly result in unsatisfying precipitation estimation. The reanalysis precipitation datasets perform better than satellite products in this region. As mentioned before, neural networks have been applied to infrared rain estimation for decades. However, one major limitation of these products is that passive microwave and infrared data are not essentially integrated as a whole to estimate precipitation. Therefore, these products are mainly based on infrared information, which curbs further improvement of precipitation accuracy. In summary, current satellite precipitation products have some common weaknesses, including inaccurate snow estimates, low quality precipitation retrieval in high latitude, in passive microwave and infrared data. Deep learning techniques provide new choices to resolve these problems. This study used the coincidences between GPM and the CloudSet satellites, and is designed to explore whether deep neural networks are able to mitigate the aforementioned problems. To be brief, spaceborne radar data are used to train passive microwave, infrared, and environmental data for rain and snow estimation in high latitudes. Understanding the quality of spaceborne radars is necessary before we apply it to deep neural networks. We conducted an intercomparison between CPR, DPR, and PR, and the paper was published on WR in global precipitation distributions of the three radars are shown in the two figures. We used all the data available in their coexisting period. DPR and PR agreed well with each other in terms of spatial patterns in the tropical and subtropical regions. The differences between them is generally smaller than 0.05 millimeters per hour. CPR shows high precipitation on the high latitude ocean and is relatively lighter precipitation on the tropical region. The left figure illustrates the mean global snowfall distribution for CloudSat CPR and GPM DPR. Overall, global snowfall was mainly distributed at high latitudes, particularly in the zones along snow enough to produce much snow in cold seasons. However, snowfall of DPR was much broader in comparison with that of CPR. Considering that CPR is more sensitive to light precipitation and snowfall, we suppose that the phenomenon is caused by the limited snowfall samples of CPR. In addition to high latitudes, snowfall can also occur where altitude is high enough. The DPR snowfall map indicates that the Cordillera Mountains has the highest snowfall in low latitudes. According to the scatter plot, CPR produced a larger amount of light snowfall events than DPR, and DPR underestimates the snowfall rate by 13%. We also used the highly dense hourly gauge networks in China to evaluate whether TrimPR and GPM DPR can capture precipitation over China. Coincident samples between radars and gauges are derived. A coincident event is defined as an occasion where both radar and gauge products have observations in the same grid. The figure shows the distribution of gauges and coincident samples in China. Data from more than 30,000 gauges are used. As shown in the scatter density plot, both PR and DPR correlate well with hourly rain gauge data, and the correlation increases with the increase of rain rate. Distribution of match-up events is highly scattered. We assume that the limited capability of gauges in measuring light precipitation will largely contribute to the weak correlation between gauges and radars. That means radars could perform better than the figure shows. After the evaluation, we explored using deep neural networks to retrieve rain and snow using multi-sensor and reanalysis data. The paper was published on WRI in 2018. The table summarizes data sets used in this study. More than 10 types of data sets from different sources are used. The study used data from GPM DPR and CloudSat CPR to train GMI, which is the microwave imager. Therefore, it is necessary to acquire coincident samples between CloudSat and GPM. Fortunately, a product has provided the coincident samples. Data from GMI, DPR, and CPR, as well as some auxiliary datasets are included. The period is from 2014 to 2016. GMI brightness temperature is provided by the product 1C GPM with 13 channels from 10 to 183 GHz. GMI level 2 precipitation and the frozen precipitation are from 2A G-proof GMI. The G-proof algorithm is responsible for retrieving passive microwave precipitation for the GPM mission. This algorithm supports the retrieval of more than 10 sensors, 10 passive microwave sensors. TPR precipitation data are from 2A DPR. CloudSat rainfall products include 2C precip and 2C rain. And 2C snow is the snowfall product of CloudSat CPR. Furthermore, MODIS and ECMWF data are also included in this study. This data from 2014 and to 2016 are used to train DNN, and we also acquired orbital data in 2017 for the totally independent validation. The spatial distributions of coincident sample numbers between CPR and GMI is shown. The study area was restricted to high latitude regions between 50 and 70 degrees because the samples are inadequate at low latitudes and the GPM satellite can only reach 70 degrees. Since the horizontal resolutions of GPMI, DPR, and CPR are different, there are often more than one CPR or DPR pixels corresponding to a specific GMI pixel. Data for these CPR or DPR pixels are averaged to match the data for the corresponding GMI pixel. The flowchart describes the main procedures of this study. First, DNA input and the reference data sets were produced by combining CloudSat, GPM, MODIS, and the ECMWF data. Second, were trained from 2014 to 2016 based on various scenarios. Finally, high latitude GMI rain and snow were estimated based on the best performing DNN, and the results were compared to ERA injury and MER2 reanalysis datasets. Although DNA is able to extract features automatically, we designed two training groups in this study to explore the advantages and disadvantages of different channels. Our objective is not only to obtain an optimized network, but also try to obtain some physical knowledge which is meaningful for the development of physically based algorithms. Passive microwave data from GMI, infrared data from MODIS, and environmental data from ECMWF. The combination of GMI and MODIS data is helpful to explore whether infrared brightness temperature can provide complementary information to passive microwave observations. The answer to this question may recommend joint passive microwave infrared retrieval in the future. The inclusion of ECMWF data might also be helpful to improve the accuracy of precipitation estimates. We used two environmental variables, their air temperature and the total precipitable water. The first group shown in this table is designed to explore the advantages of different GMI channels and the effectiveness of combined passive microwave, infrared, and environmental data. Group 2 is used to demonstrate the capability of infrared data in estimating precipitation. Moreover, because GMI have certain channels, some channel combinations can imitate other passive microwave sensors, which enables a preliminary investigation to the performance of other sensors. A 4-layer fully connected deep neural network was used in this study. The input layers receive inputs from the two training groups. For different scenarios, the number of input neurons range between 2 and 17. The have 30 neurons. The number of coincident samples between CloudSat and the GPM limits the complexity of DNN because a too wide or deeper structure has a high risk of overfitting due to the too many parameters and the inadequate samples. Actually, our recent work based on MHS, another passive microwave sensor, has much more samples, which enables us to design a more complex neural network, and the results are satisfying, but we don't include these results in these slides. The output layer only has one neuron, sending out rain or snow data that are trained to the reference datasets. We cannot apply CNN or RN or LSTM in this study because the inputs are not continuous in space and time. These samples distribute in the global scale, and actually they don't have very clear connection with each other. The DN was trained separately for land and ocean in this study because their different background emissivity characteristics have notable effects on precipitation retrieval. The training method is the LM algorithm, which blends the speediest descent method and the Gauss-Newton algorithm. Actually, the widely used optimization method in Python is not very suitable to this network because we found the results are not very good. However, for a large-sized networks, the LM algorithm would fail because the metrics in calculation will be highly time-consuming and occupy too much memory space. The scatter density plots compare the rain and the snow of CPR, DPR, and GMI. We can find that both DPR and GMI agrees well with CPR. However, both GMI and DPR underestimate the rain rates with relatively bias up to -50%. For snow, the correlation coefficient between GMI and the relatively bias is also very large. This slide shows the occurrence frequencies of DPR and GPI at high latitude. DPR and GMI show similar frequency curves for moderate to heavy precipitation. However, for light precipitation, the threshold of the probability of precipitation has a notable effect. By combining data from GPM, DPR, and CloudSet CPR, we generate a reference rainfall and snowfall dataset that can cover both land and ocean. Some critical issues are addressed during the training and the testing of DNN. The first issue is which CloudSet rain product should be used. We have mentioned that CloudSet produces two rain products, which are 2C rain and 2C precip. For the training and the testing of DNN, the performance of the two products is similar with each other, except that 2C precip has much more rain events between 0.2 and 2 millimeters per hour. Therefore, just relying on the training or testing of the neural network sometimes can not fully reveal the difference between the two reference datasets. We further applied DNN to GMI rain estimation in 2017. This is not just a research experiment. It is more like the operational production of GMI products. The data volume is so large that the samples used in can be neglected. Results show that DNN based on 2C precip resulted in large overestimation. In contrast, 2C rain performed much better, and this is probably because 2C rain implements more realistic assumptions on the vertical distribution of rainwater and the raindrop size distribution. Therefore, in this study, we adopted 2C rain. With regard to the second issue, neural networks often generate many tiny precipitation estimates, which should be zero in most cases. Of course, we can set these tiny estimates to 0, but it is difficult to decide a reasonable threshold. In addition, your network may underestimate the frequency of heavy precipitation, like the correct this problem. We adopted a probability matching method based on the cumulative density function. As shown in the figure, for moderate to heavy precipitation, DNN agrees better with the reference datasets compared to gproof. However, the frequency of the pre-adjusted DNN light precipitation is too high. After the CDF adjustment, the curves of DNN rain and snow almost overlap the curves of reference datasets. The third issue is about how much improvement is gained by merging CPR and DPR. And of course, the answer is positive, and we'll just come to the fourth issue. The preprocessing of precipitation means that rain and snow, thus DNN can directly produce rain and snow using brightness temperature as input. For post-processing, total precipitation is trained first, and then the DNN outputs are partitioned into rain and snow using temperature data, which is common in precipitation algorithms. The figure compares the performance of pre-processing and post-processing. We find that pre-processing is always better at snow estimation. Therefore, the pre-processing strategy was adopted in this study. The success of pre-processing strategy in snow estimation suggests that GMI passive microwave data already contains sufficient information for snowfall retrieval without the need for data. The slide shows the metrics of precipitation estimates from gproof algorithm and the DNN in the training and testing periods. The DNN outperforms gproof for almost all metrics for land and ocean. The improvement in snow estimation is much more significant. For example, over oceans, the correlation coefficient was improved from 0.28 of GMI to more than 0.7 of DNN. The addition of MODIS and ECMWF data can further improve the accuracy of rain and snow estimation. The Taylor diagram compares training group 1. The distance between the points and the OBS point is inversely proportional to their quality. The low frequency GMI 1 to 5 is good for rain estimation over oceans, as shown in figure 8. But it is the worst for snow estimation over oceans and snow estimation over land, because these estimates rely heavily on information from high-frequency channels. The mid-frequency GMI 6 to 9 is good at both rain and snow estimation. The high-frequency GMI 10 to 13 is best at snow estimation, but worst at rain estimation over oceans, because a large fraction of rain over oceans is from shallow systems, ice aloft, and thus little scattering signal. GMI 1 to 13, which uses all the channels, is constantly better than any other scenarios with incomplete GMI channels. This slide is based on training group 2. Main conclusions are infrared channels beyond the commonly used 10 to 12 micrometers can also contribute to the improvements of precipitation retrieval. And second, TMI and SSMI performed similarly to each other. The results prove that the values of DN is not only to establish the relationship between input data and precipitation. It can also reveal some implicit. Interesting application is to use DN to explore the optimal channel combinations for estimating rain and snow under different surface types. To validate the effectiveness of the optimized DN, precipitation is estimated based on GMI brightness temperature and reanalysis environmental data in 2017. Reanalysis precipitation data are used to evaluate the accuracy of DN and G-proof estimates because it is acknowledged that reanalysis data is better than satellite data in high latitudes. This slide compares the precipitation estimates of G-proof, DNN, ER interim, and MER2 following event in 2000 with rain and snow at the same time. The precipitation extents of the DN and G-proof are similar with the two separate rain bands in the southern and central parts. EI interim and MER2 show similar precipitation patterns. The DN enhances both rain and snow rates compared to G-proof and is closer to the reanalysis dataset. There are more than 5,000 GMI orbits in 2017. For each orbit, we calculate their metrics and show them in the box below. This figure summarizes the metrics of rainfall. We can notice that there are two DNs. DN1 only uses GMI brightness temperature as input, and DN2 uses both GMI and environmental data. Reduced the underestimation of G-proof. With regard to snow, DN are almost always better than G-proof concerning almost all metrics over land and ocean. For example, the correlation coefficient over land is improved from 0.28 of G-proof to 0.53 for DN2. These tables summarize some metrics of, and actually this metrics has been presented in the above slides, so we will just pass this slide. Although reanalysis data sets were used to assess the performance, they also contain some uncertainties. Therefore, we adopted the triple collocation method to analyze the errors of precipitation estimates. I will use TC to represent the triple collocation shown. TC can obtain error estimates of three independent products without the need for the true value. Previous studies have shown the effectiveness of the triple collocation method in precipitation evaluation. Our paper published on Journal of Hydrology validated the accuracy of TC by using very dense gauge networks. The results demonstrate that the TC method is reliable because the metrics derived from TC are close to those derived from ground observations, with the relative differences. This slide shows the correlation coefficients based on triple collocation. DN performs much better than G-proof, and the patterns are similar to the analysis based on the reanalysis data. For rain, DN1 and DN2 are generally better than G-proof, particularly over oceans. However, the correlation coefficient of DN2 is worse than DN1 in the southern hemisphere. Actually, we expect better results of DN2 because it involves both brightness temperature and environmental data. So this is a problem that needs further investigation. For snow, DN2 is excellent and better than G-proof and DN1 in the globe. Spatial distributions of rain are shown in this slide. Reanalysis datasets show similar patterns. Compared with them, G-proof notably underestimates rain over the oceans, but IMERGE significantly overestimates rain over oceans. Deep neural networks agrees well with reanalysis datasets. For example, the DN mean rain rates in the Northern Pacific Ocean, the western coast of North America, and Greenland show values that are more comparable to reanalysis than G-proof. DN2 produces stronger rain rates than DN1 over the oceans and Europe. In contrast, DN2 rain rate is weaker than DN1 in the mountainous regions along the western coast of North America, probably because the quality of was in complex terrain and more precipitation is identified as snow. It should be noted that similar to CUAHSI and the reanalysis data, the DN shows a clear precipitation gradient around the 70° north over Atlantic Ocean. G-proof also captures this gradient, but with lower intensities. For snow distribution, the G-proof mean snow rate is very low at high latitudes. IMERGE produces higher snow intensity than G-proof, but overestimates snow in regions around 60° south. The DN enhanced snow intensity, particularly over oceans in the southern hemisphere, compared to G-proof and IMERGE. ERA interim and mirror. In addition, in Greenland, the DN produces much heavier snow than adjacent areas similar to reanalysis datasets. This feature is not noticed in G-proof. And particularly, DN2 produces heavy snowfall along the western coast of North America, which partly explains its low rain rates in this region. On the whole, the spatial distributions of DN are more reasonable and closer to reanalysis datasets. Finally, the main conclusions are summarized in this slide. In the training and the testing of networks, DN-based rain is constantly better than G-proof-based rain over high latitude land and oceans. For snow retrieval, G-proof by far. And combining infrared and environmental data with passive microwave brightness temperature contributes to better precipitation estimation. Environmental data are particularly useful in improving snow estimation accuracy. And DN is efficient in reflecting the general physical mechanisms of precipitation retrieval. GMI rain and snow in 2017 are estimated based on two types of DN using inputs from GMI and ECMWF. The merit scores and the spatial distributions of DN are much better than GPM products. Thank you for attention, and the questions are welcome.
If anyone has any questions, please type it into the chat box and we'll read it out loud to be answered.
Hello?
So while we're waiting for questions, unless Kwai, if you have something, I want to talk more about the rest of the series.
Yep. Can you guys hear me? Can you hear me?
Yes.
Okay. So hello everyone. I'm quite fun work with Dr. Chao Fengshen, who has to leave a little bit earlier for this seminar. And to the presenter, I do have one question about, there's one bar plot showing the test error versus the training error. And we all know that one drawback for deep learning model is that the overfitting issue. But I noticed that in this research, the testing error is almost similar than to the training error and sometimes even smaller. So I'm wondering if the author can share some insights about the regulation techniques or the way to avoid the overfitting issues.
Actually, we used 60% of the data for the training and 20% data for validation and 20% data for the final evaluation. So in the training of the deep neural networks, there are always 20% data remains to be validated to avoid overfitting.
Sorry, I don't really understand what is your validation side will do. I mean, so what is the validation process?
When we train the neural networks using the 60% data, we calculate the such as the mean square error, and the neural networks tend to minimize the objective function. And at the same time, we have 20% data for validation, and then the neural network also calculate the mean square error for the 20% data, and once the mean square error for this 20% data don't decrease anymore, the training process avoid overfitting.
Okay, I see. It's like the early stop.
Yeah, the neural network is actually it won't minimize the objective function of the training data. It tries to get a balance between the training data set and the validation data set to avoid the overfitting.
Okay, thanks. So are there any more questions? At least I think they're almost done with time, right?
Yeah, so if there's any questions, let me actually bring some attention to something else. Hold on one second. I'm going to take back presenter mode. And I'm going to show my second screen. So I just want to bring to everyone's attention, we have 2 more webinars coming up in this series. So next Friday will be Jordan Reed and Vipin Kumar. They will be talking about process-guided deep learning. And then the final one will be on May 10th with Qualin. He's going to do remote sensing precipitation. And just want to tell everyone else as well that CUAHSI has a conference on hydroinformatics coming up at the end of July, and we do encourage you to submit an abstract for an oral or poster presentation by April 30th. And for those of you who are students or postdocs, we are offering $750 travel grants on a first-come, first-served basis. So please do submit an abstract. We do have plenty of grants left there, so please take advantage of that. And then for everyone else, registration deadlines, early birds June 15th, and then the final deadline will be July 15th. And Chao Peng will also be a keynote speaker there, as well as other people like Neben from University of Central Florida and Gene Shawcroft from Central Utah Water Conservancy District. So it's a very diverse set of speakers for keynotes as well as sessions. So with that, I don't think there's any more questions. So thank you for coming. Oops, actually, one just popped up.
Oh, really? Okay. Oh, hi, Dr. Tang. There's a question from Chao Shen, and Can you elaborate more about how did you control the uncertainty in the model besides minimize the RMSE? So this question is about control the uncertainty of the model.
You mean how I control the?
Yes. Yes. Did you like consider the uncertainty?
Actually, I don't understand the question fully. Because we can get different results if we have different random seeds or the different training epochs or other hyperparameters. So I'm not very sure what this question means.
Okay. To me, I think it basically means that how you train a model to be robust. So I think it's similar to my question, how you train the model to minimize the difference, the overfitting issue. So I think the early stop in the validation set is
actually
really works for the model.
Actually, we have some principles, and when the MSE for the validation set stopped decreasing for 6 steps, the model is stopped, and I mean the training process is stopped. So just some simple principles that are used by all kinds of networks. So yeah.
Okay. So hi Chaosheng, did you think you got the answer for the question? And I'm wondering if there are any more questions. Okay. Oh, there's another one, and from John. Sorry. I'll raise a question. In order to use the DNN, did you check the probability distribution of precipitation so you can ensure the entire range is used in the training process? If so, how DNN deals with higher value out of the range using in the training validation process? I think it's really good question.
Sorry, can you repeat the question? I just have a bad connection.
Dr. Tang, I think you can see the question in the chat panel. So
I will see it.
Audience is asking, have you checked the probability distribution of the precipitation? So the training set kind of cover the whole distribution.
Actually, I have mentioned that we conducted a CDF correction to the outputs of DNN because DNN always generates too many low values and may tend to underestimate the frequency of heavy precipitation. So our answer is that we can further adopt a correction method like the CDF matching method to adjust the precipitation. And currently, we didn't solve the problem that the deep neural network cannot always generate very high cannot generate cannot achieve good simulation of the extreme precipitation and also reduce the tiny precipitation rates. So we think the CDF correction should be a good choice.
Thanks. So Johanna, do you have further questions? So Johanna just type in that, Dr. Tang, do you think it is a common drawback in the machine learning models or very specific of this specific technique?
Yeah, actually, I think so. It is hard to acquire good results for extreme events. I mean, extreme large and extremely small. It's difficult for neural networks to get quite good results.
Okay, guys, I think we are running out of time, and I want to thank Dr. Tang for the presentation, and thanks everyone to come, and let's call it a day. Thank you, everyone.